On the scalability front, it's essential that we provide blockchain-based services to people at really large scale.
Here's Emin, a professor at Cornell University who's currently visiting EPFL.
For example, if we were to try to use Bitcoin as it is right now, with its initial parameters set by Satoshi Nakamoto, we would be able to support about 3 transactions per second. 3 transactions per second is about the number of transactions that you get at a very busy department store in Zurich on a weekend, right? It's a very low rate.
In other words, Bitcoin does not scale.
People often talk about getting nations on Bitcoin. It's not going to happen with this technology for the simple reason that, let's suppose, if all of Venezuela were to switch to Bitcoin right now, every adult would get to transact once every 36 days. You buy a packet of gum, you can't buy bread the next day.
This is not ideal.
The scale is inherently limited in these protocols, and it's limited by design. So there's the decision-making granularity is a block. A block has to have a maximum size. If you made them too big, then the system would be subject to other attacks. As a result, we are in a situation where we would have a fixed size block appearing every block interval, and for Bitcoin it comes out to 3 transactions per second.
Now, Bitcoin is not the only blockchain-based cryptocurrency.
More modern blockchains, like Ethereum, which is based in at the Ethereum Foundation in Zug here in Switzerland. In Ethereum, they are much more aggressive with at least the block interval and also the block size, and they get about 7 to 25 transactions per second.
This is better, but not good enough.
Neither of these are anywhere near enough. If you want to compete with Visa, Visa's regular average transaction rate on a day like this, which I think is a Tuesday or on a regular November day, it's no special day, about 2,000 transactions per second. So we need to add 3 zeros to our systems. Visa's peak ability is about 50,000 transactions per second, and we should be able to get to that level if we want to really compete with Visa on Black Friday, which is a concept that some people might not be familiar with, but that's the peak shopping day in America, is the day after Thanksgiving, where everyone's out there trying to buy Christmas gifts. So those are the numbers we have to meet, and you can see that there's a 3 to 4 order magnitude gap between them.
So how can we get the blockchain to scale?
So there are 2 different approaches to fixing the scale problem. My group has been at the forefront of both of these approaches. So the first one is called on-chain scaling. That is, we try to push the chain to its limits. And we were the first ones to look at this problem from a scientific perspective. There was a lot of hand-wringing and debate in the Bitcoin community over how to reparameterize Bitcoin. And what if we make the block size a little bigger? What if we change the block interval a tiny bit, and so forth? We can adjust those parameters, but parameter tweaking, for one, is completely unsatisfactory from an engineering perspective. This is not what an engineer does. You don't tweak parameters just to see what happens afterwards. That's exactly how you get bridges that break down. Right? Let's try to push the limits. Oh, did not work. Right? So that is not an acceptable starting position. It's the wrong mindset entirely.
Just to recall, all of Bitcoin is now worth a few $100 billion. Glitches in the Bitcoin protocol might lead to a huge loss of some of these $100 billion. So we are really no longer at a point where we can tweak the parameters of the Bitcoin protocol.
Also, the debate was being waged in very unscientific terms. Essentially, these parameter tweakers, they have qualitative arguments and trying to make a quantitative point. This is not science. So one of our main approaches, or one of the freshest things we brought to this space, was essentially to say, this is a scientific question. We have to go about it using proper scientific techniques. What are the metrics? What's our goal? And so we established a set of metrics for consensus protocols and defined them precisely. We collected data from the actual networks. We built a simulation framework for large-scale blockchains where we could test hypotheses in the lab in identical conditions to the actual, the wild internet. So with that infrastructure in place, we looked at the problem in depth, and it became very clear to us what was wrong with Satoshi Nakamoto's consensus algorithm. In a nutshell, it's fairly straightforward. This protocol makes a decision every block interval, and then goes into a frenetic mode where it shares that block with everybody else.
Let me remind you that the Bitcoin block to be added is roughly 1 megabyte. It's not that easy to get this 1 megabyte to get through all the mining nodes of the internet.
There's no need to understand the underlying technology to see the problem, right? Imagine that you have somebody in London trying to add a page to a ledger that we share across New York, Zurich, Sydney, etc. Everyone would have to go into frenetic mode to try to get a copy as soon as they can. And if the largest number of pages are being added in London, you would find business slowly navigating closer and closer to London until everybody is in London, because you have an edge over your competition the closer you are to the source that's adding these pages. So that's terrible. That now we once started with a decentralized system, and we found ourselves, due to natural pressures, sort of circling on the same center. We needed to get closer. And so that's the dilemma. So how do we get scale without creating that centralization pressure?
So how can we avoid this frenetic activity?
Instead of a retrospective algorithm, we developed a completely different style where we pick a leader, and that leader then determines the contents of the page on the fly in a forward-looking fashion. So instead of saying, in the last 10 minutes, here is what happened, and then sending a giant page to be shared among all the participants, what we do is the exact opposite. We select somebody, and that person in real time, as transactions come in, he vets them and creates a well-ordered sequence saying, this happened, and then this happened, and then this happened, and then this happened. So now you have transactions 1, 2, 3, 4 that were issued into the system, vetted by the record keeper, and serialized into a proper format, but without the frenetic activity that normally accompanies a giant block. So all of the blocks, all of the messages that got sent are small and incremental, and they happen in real time.
This trick also allows to solve the delay problem in Bitcoin.
Normally with Bitcoin, there would be a 10-minute delay from the issuance of a transaction to its inclusion in a block. Whereas with our approach, that thing gets included in what we call a microblock, in a vetted tiny little message that's been signed by this record keeper, by the leader, in almost instantaneously in a sub-second with sub-second latencies. So this completely changes the game. We sidestep the entire block size issue. There's no issue of a block size because we don't have backwards-looking blocks. We don't have to get a giant block from London to Sydney to Zurich and so forth, because there's no giant block. What instead you have are trains of small messages that are coming out and going out to wherever the respective listeners are. And at some point, through the same process that governs Bitcoin's block creation, another record keeper is chosen. So suppose the London person got elected and he made a gazillion, let's say hundreds of thousands of microtransactions, and then the next person is in Zurich, and then he takes over. He will end up cutting off perhaps some number of transactions that the person in London issued that he hasn't yet heard of. And that's okay. The protocol is designed to be resilient to that. And most importantly, he avoids this frenetic activity, and therefore it allows the system to gain enormously in terms of latency and also in terms of throughput. So we've shown with the experimental framework that we have that this system can achieve about 300 transactions per second instead of the 3 transactions per second. So that's 2 orders of magnitude.
This protocol is now being carried out in practice.
The system has been deployed in Russia recently. So Burger King, of all places, was one of the very first commercial deployments to deploy a blockchain in a real business application. They keep track of loyalty points. So the more burgers you eat, the more loyalty points you collect, and at some point you get to redeem them, etc. So it's some kind of a common, typical thing that companies do. It's essential for them to be able to record more than 3 transactions per second, of course. They need high scale. And for this, they used our protocol. And so this, what we call the NG, the next generation protocol. So they have something called Waves NG that embodies this. That gets somewhere around 5,000 transactions per second within their deployment. So we were conservative in our measurements. They managed to get much better numbers.
There are many criticisms of Bitcoin. Some people criticize the loss of energy which is which is used by all the computers doing the mining to maintain the Bitcoin network.
But we would really like to even scale it higher than the numbers I quoted you before, 2 to 5,000 and then max of 50,000. We'd like to go to millions of transactions per second.